Well, hi again, this is Bob, and we're getting ready to look at section 6.2, which I think is one of the more or most interesting lessons that we're going to run into in terms of this normal distribution and being able to make predictions or inferences from the standard normal distribution. And I'd like you to make sure that you've read through the material on 6.2. I decided to break the section into two parts just to make it a little easier instead of going all the way through. And we're going back to chapter 3 now a little bit when we had a test question on this also, where we may not have known what we were doing, but we calculated, or we had a formula to calculate z-values. And we had like a value from a set, and from that we subtracted the mean, and then we divided the whole thing by the standard deviation. Okay, and in symbols, there's our x, member of the set, minus our population mean divided by the standard deviation. Okay, now before we go any further, I wanted to carefully, since we just were introduced to these tables in the last lesson, I wanted to reproduce this at the bottom. It's not the best graph, but it doesn't have to be. I wanted to do a few of these. I wanted to show how it is that we, I keep saying that the mean is our symmetry line there, where z is equal to 0. And I wanted to just do maybe 2 or 3 calculations to reinforce that with the standard curve they've given us toward the bottom of page 328. And if you notice there, the situation is, we had the scores for a standardized test, and they were normally distributed. And the scores had a mean of 100 and a standard deviation of 115. All right, so whatever it was, we don't know the total number of points possible or whatever, although we could, kind of get a pretty close guess. But we know that the mean was 100. And if you've noticed, they've written 100 under 0 for our z-value of 0. And they told us also that the standard deviation for the test was 15. So we're going to try to relate all this together here. Now, if you notice, what I've done is I've added 15, then added 15. In other words, our test scores, just these in between here, and I'll throw some lines there for standard deviation. And I want to relate this to the formula I just copied here. And remember that our, in this particular example, our mean was 100 because they told us to, and they told us our standard deviation was 15. Well, let's see, first of all, how we get a z-value of 0 for the mean. I've mentioned it before, but that calculation would be z equals 100, test score of 100. Somebody had a test score of 100, minus 100, divided by standard deviation of 15. Hopefully now we can see that a test score of 100 would give us a z-value of 0. Okay? And I can squeeze one in at the bottom here. Let's see what a test score of 115 would give us. Well, that turns out to give us 15 over 15, or 1, and that's why we have a 1. We know why we have the 0. And now we know why we have 1 standard deviation at 115. We can show that on our z-value, our z-values. And let's do one more of these here. Let's find out what a score of 85 would be. Well, that turns out to give minus 15 over 15, or a z of negative 1. And sure enough, when we go back and look at this graph here, we had a 1 at 115, we had a z of 0 at 100, and we got a minus 1 when our test score was 85. Okay, so hopefully now that will help relate the z-values to the scores. And the neatest thing about this is here we've used a standard curve, normal distribution, to talk about test scores. But what they're telling us in the rest of this section, for example, on 6.6, they're telling us we can use that exact same standard normal distribution to make predictions or inferences about liters of blood in a person's body. Or we're going to look at 6.7 also, monthly newspaper recycling. And on 6.8, we're going to use the same curve to talk about decibels at a concert. So, you know, usually the first thing that an algebra teacher mentions at the beginning of a class is that you can't compare apples and oranges. But it's interesting, in statistics, we use the same normal distribution here to describe or make predictions from a number of different situations. Now, there are some restrictions or some things we need to do before we go use this curve, and they'll talk about that later, actually pretty soon here. So I thought what I'd do is I'm going to concentrate, since we now know how to use the z-tables and took some extra time on them, I'm just going to concentrate on the usage of the tables, and I'm going to strongly encourage you to review the calculations, because I don't need to go through the calculations again, because I stressed that in section 6.1. Anyway, I'm at the top of page 329, and it says, since we now have the ability to find the area under the standard normal curve, that's 6.1, we can find area under any normal curve by transforming the values of the variable to z-values, and then find the area under the standard normal distribution, as shown in section 6.1. Okay, so we've got a little procedure table there, and notice the first one, draw the situation. Draw a normal curve and shade in the desired area. Then use our formula to calculate the z-value, and then find the corresponding area. We're going to use tables, but there is software, and many calculators have those values built in also. Okay, so let's start off with example 6.6, which is liters of blood. All right, now we just used the standard normal curve to make some predictions or discuss test scores, and now we're using it for liters of blood. And it tells us that an average adult has 5.2 liters of blood, and assume that the variable, in other words, the liters of blood in the average adult, is normally distributed. And what that means, of course, is that some people have more than 5.2, some people have less than 5.2 liters of blood, but they average out, and that averaging out means the bell curve. Okay, so we're going to pick a person at random. Let's see, it says, assume the variable is normally distributed and has a standard deviation of 0.3. Find the percentage of people who have less than 5.4 liters of blood in their system. Okay, so here's our situation. Our mean is, by the way, that's a z of 0, but I'm going to start off by writing 5.2 here, which is the mean amount of blood for the average adult. And what we want to do is find out the percentage of people that have less than 5.4 liters. And of course, that's a little more than the mean. Okay, and everything to the less, or excuse me, everything less would be the area to the left of 5.4. So this is the area that we're looking for. It's our desired area. And of course, as soon as we get some z-values, we can find that area out directly because our tables will tell us. But we can't do anything until we find out the z-value associated with 5.4. So I'm going to put some things that we know here. We know that the mean is 5.2. We know our value that our variable that's normally distributed is 5.4, and we know our population standard deviation, I believe, was 0.3. Yes. So let's get the z-value. So our z-value would be 5.4 minus 5.2 divided by 0.3. And they tell us that that's 0.67. Okay, so keep in mind, of course, that our z-value at the mean is 0, and our z-value at the 5.4 liters is 0.67. All right, so to find that percentage of people that have less than 5.4 liters of blood, what we would do is we would go to our tables. I'll put that new situation, which they did, but I'm going to use the book's answer. Okay, and we can read that directly, and they tell us that that area is 0.7486. Or then they tell us that therefore, if the area is 0.7486, then we can assume that 74.86 of adults have less than 5.4 liters of blood in their system. So what we just did is we converted and found a z-value, then we converted that z-value into an area, and then we converted that area into a percent to summarize our results. All right, well, let's take a look at the next one. I'd like you to be sure you verify the calculations in the z-table there. This is a couple of different questions. It's about monthly newspaper recycling. Okay, and so far we've talked about test scores, liters of blood, and now a completely different subject, but which we can still use the standard normal distribution. It says each month, this is top of page 330, it says each month an American household generates about 28 pounds of newspaper for garbage or recycling. We assume the variable is approximately normally distributed. That's another way of saying that we can use our tables, the z-tables, and that the garbage, assume the variable is approximately normally distributed and the standard deviation is 2. And then we're going to take a household at random and find the probability that it generates between 27 and 31 pounds of newspaper for garbage or recycling per month, or more than 30.2 pounds per month. So let's write some things here. We know that our mean is 28 pounds, and our standard deviation is 2 pounds. And our first value between 27 and 31 pounds per month. Okay, so what we're looking for, let's draw a little diagram here. Well, I should really here put 28. Okay, now the first one is between 27 and 31, so 27 would be below the mean, and of course 31 would be above the mean. Now, my drawing is not good but it's more than good enough for us to find this requested area here. And that requested area then immediately becomes our answer, because it's going to give us the probability, which is like a decimal or percent of the given households generating between 27 and 31 pounds a month. However, before we could do anything, I do know that 28 is going to have a Z of 0. Before we can do anything like going to the tables and apply what we learned in 6.1, we've got to find the Z value associated with 27 pounds and 31 pounds. But that should not be difficult, since we know that the mean is 28. So the first one, we'll do the negative one first. 27 minus 28 over our standard deviation of 2. And that's going to equal minus a half, or minus 0.5. Okay, I'll bring this all up on the next one there, next page. And our positive Z value would be 31 minus 28 over 2, or 3 over 2, or a Z of 1.5. So here's what we're really dealing with. Got everything turned into Z values. My drawing hasn't gotten any better, but it doesn't have to, because it's just a little representation of what's happening. We want the area between a Z of 1.5 and negative 0.5. And we've seen this situation before. What we're going to do is find the area, all the area to the left of 1.5, and then subtract the area to the left of negative 0.5, okay? And let's see here. The book does that for us. Over on the top of page 331, wait, I want to make sure I didn't get ahead of myself here. Oh, they just went ahead. I take that back. That's in their step 3 there. The area to the left of what they call Z2 is 0.9332. And then the area to the left of what they call Z1 is 0.3085. And that difference there is 0.6247. And summarizing our results, we can say the probability that a randomly selected household generates between 27 and 31 pounds of newspapers per month is 62.47%. Remember, we're going to just go ahead and change the area to a decimal, or excuse me, to a percent. Okay, and whether they recycle or not, we know that the probability that somebody generates that amount of trash is 62.47%. Okay, so we've done it with, used that curve for test scores, and we've used it for liters of blood. Oh, we got one more to do, and now we're doing trash. Let's do the last one here. This was part B, more than 30.2 pounds per month. So we'll go back to our original drawing. The average person does 28, generates that much. You know, that may or may not be true nowadays with so many newspapers dying off and people reading their news online. But this one says more than 30.2 pounds per month. So I'll say that 30.2 is about right there, and this is what we're looking for, okay? And recall that our mean was 28, and our standard deviation was 2 pounds. Okay, well, we've seen this situation before. We've got to get a z-value associated with 30.2, and we do that by going z equals 30.2 minus 28 divided by 2. So that's 2.2 over 2, or a z of 1.1. So I'll go to the top of the next page. Now we're back in chapter 6, section 6.1. So more than 30.2, represented as 1.1 as a z-value, would be everything to the right of 1.1. This, of course, would be less than 30.2. This would be more than 30.2. Okay, so what we do is we find everything to the left of a z of 1.1, and then we subtract it from 1. And when I say everything to the left, of course, I mean the area. And I'm going to take the book's word that that is 0.8463. And that difference then would be 0.1357. Okay. Well, I'm going to do one more question here, and then I'm going to cut the lesson in half and come back shortly and do the second part of 6.2. And the last one is example 6.8. And that's at the bottom of page 331. And now we're talking about decibels at a concert. And they tell us it's a measure of intensity of sound, and the average number of decibels at a concert, a full concert, is 120. Well, there's some information right there. Okay? And by the way, I can also, if I want, 120 is the mean, population mean. Assume the variable is normally distributed. Some concerts will have more than 120 decibels, some will have less. And the standard deviation is 6. Okay, so we're supposed to find the, if 100 concerts are selected, approximately how many will have a decimal level less than 112. Okay, now this is just a little bit of a twist here. 112 is obviously going to be associated with a negative z-value, and we've got two parts of the problem, but it's going to turn out to be pretty straightforward. The 112 will convert to a z-value and find its area as a decimal. And if we multiply that times 100, it will tell us the number of concerts out of 100 that would have decimals less than 112. It's wordy, but we'll do it the right way. So this is going to be later here. Let's just concentrate on our answer. So what we would need to do is find the z-value associated with 112 decibels. 112 minus 120 over 6, and that of course would be minus 8 over 6, and that would be minus 1.33. Okay, so let's change to our new situation. Now, let's find this decimal, and the book has done it for us, and we'll take their word for it. They say that that area represented is 0.0918. Well, you know what? That's about 9%. Okay? About 9% of the concerts have less than got the number already, 112 decibels as the average intensity. So remember that if we had 100 concerts and about 9% of them had decibels less than 112, then we would just simply multiply those together. And you know what, I'm just going to round this, and that's fine. It turns out that it would just be 9 concerts. Now, if there were 1,000 concerts, it would be 9% of 1,000, or like 90. Okay, if there were 10 concerts, it would be like 1 concert, or the closest that we could get, about between 9 and 1%. But 100 concerts, and the probability, or our area associated with negative 1.33, was around 9%, and 9% of 100 would be about 9 concerts. And they summarize that at the bottom of step 3 on page 332. Approximately 9 concerts out of 100 would have a decibel output less than 112. Okay, anyway, I will be back shortly with the rest of 6.2, and we will see another formula. It's a pretty straightforward formula, but in order to use it, you have to be able to go from an area to a z-value. And of course, we did a lot of practice on that in 6.1. So I will be back shortly. Thank you.